sorry. Hmm. Okay. Well, we don't want you to be upset. Like, we really want you to. I mean, another what? Physics lab? I don't. I think Thursday. It conflicts with. What was it? What does it complete? Gosh, we weren't considering geomatics. I'm sorry. Sorry, guys, because there are only like a half dozen of y'all. There's more than that, actually. But we have like 100 biology majors that we have to consider. So you guys are important. Absolutely. Absolutely, you're important. Okay. But anyway, there are a lot of pieces that come and fit together. But in the end, we always get everybody taken care of. All right. So we'll get you taken care of. And worst case is that you just wait to take the lab for a later semester, and that's okay. That doesn't really throw a kink in your other courses. It doesn't prohibit you from taking other courses, unless, of course, you're trying to graduate before then. But see me if that's the case, and we'll deal with it. Um, let's see. I do want to show you. I sent this out on email yesterday. I put your take-home test online. It's on Moodle. I sent it out as an email. You need to do this moment of inertia. Listen, you can find this online, the derivation. You could do it on your own, I think. It's actually pretty simple because you're just taking the integral of r squared dm, and you're integrating from this point, which is your 0 point, out to this point, which is the length of the bar. So it's even simpler than the other one that we did, the bar. So if you look at that derivation, probably not a far reach to get to this, but I just want y'all to put it on paper. Write out a couple of sentences too, describing how it is that you derived that, sort of the thought process behind it. I define my, what do you call it? Your DM, your differential element that you integrated over, and then how you did that. And then I have a couple problems here. These are statics problems that we have 4 examples that we'll work through, some of which are pretty similar to these. So uh, that should help you. We'll get to that probably on Monday. And then I also sent out early this morning the very last section. We just have about a week and a half left, but the very last section on optics, which we'll get to, and that will be on the test. And I posted the homework as well. We might trim it down a little bit. Some of the stuff we might leave out just for time, but that'll be the very last chapter. Okay. You have any questions or burning issues? No? All right. Well, let's wrap up this problem we are working on. Um, what was this? This was a flywheel. Um, we had defined its moment of inertia here. We had defined the net torque that's acting on the flywheel. We have this shaft, and there's a frictional force acting on the shaft. Um, So this is the force of the friction. This is the radius of the shaft. So that's the moment arm over which that frictional force acts. So that is the net torque on this flywheel. This is the moment of inertia. So now we can find the angular acceleration by Newton's second law. Torque equals I alpha. So my alpha is torque over moment of inertia. That's 2940 Newton meters over my moment of inertia, which is 32,340. That's going to give us our angular acceleration, or deceleration as it'll be. It's 2940 over 32,340. Well, it's slowing down. It doesn't, yeah, so we'll take alpha to be negative. So that's going to be 0.09, 0.09 radians per second squared. Um, and we are taking this to be negative because it's slowing down. That means that we're also going to take the initial angular velocity, where was that? 420 revolutions per minute, to be positive. So we're going to take our angular acceleration here to be negative. Not necessarily that it's in the clockwise direction, but just really that it's opposite the angular velocity because it's slowing down. That frictional force is causing it to slow down. In the problem, there's actually no mention of whether or not this is in the clockwise or counterclockwise direction, but we're taking it to be negative just because it's opposite the angular velocity. All right, so if I have that angular velocity, go ahead and convert that into radians per second, because that's our SI unit, and that's what we have the angular acceleration in. So just take a second, convert that to radians per second, and then from that we need to figure out some way to get to theta, which is actually what the problem was asking. So what is theta? Remembering that we have our two kinematics equations, I'm going to write them over here on the side, just to help us think about it. Omega equals omega naught plus alpha t, and then theta equals omega naught t plus 1/2 alpha t squared. Did I give the time in this problem? I'm asking, yeah, so how long does it take to coast to a stop? And then what angle does it go through in that time? Let's see. All right. Anybody have this in radians per second? What, 44 radians per second? That sounds right. So remember, there are 2 pi radians in a revolution, 60 seconds in a minute, so you can convert that. And then if I want to know the time, how will I find the time? Which of these will I use to find the time? The top one, right? I already know a couple of these. I know this, I know this, and I know this. So I'm just using that to solve for time. So time is omega minus omega naught minus or divided by alpha. I know all these values, but I need to make sure that I get the assignments correctly. So here, actually, this is going to be my omega naught, and then my omega final is going to be what? I have this thing that's spinning, and it comes to a stop. It's going to be 0. So I'm going to go from omega being uh, 0 minus 44 radians per second divided by my alpha, which is negative 0.09. This is where the signs come in, but if you didn't get the signs assigned correctly, not a big deal. You just come up with a negative time. You say, oh, that doesn't really make any sense. And you would just say, well, I must have a problem with my sign. So that's going to be about 450, I think. Oh, yeah, 490, 480, 489. I'll just call it 490 seconds. So that's how long it takes to come to a rest. About 8 minutes for this frictional force to cause this flywheel to stop. And then if I want to know the angle that it goes through, I just say theta equals omega naught t plus 1/2 alpha t squared. Omega naught is 44 times 490 plus 1/2 alpha is negative 0.09. Making sure that I get the negative there times 490 squared. And then that is what it is. I don't know what the answer is. But it goes through quite a number of revolutions. That's in radians, but you would convert it to revolutions. That's a good Newton's second law problem, but it also has these kinematics problems thrown in. Likely that's what you'll find, is that you'll have this type of problem, but then I ask you stuff about its motion, its angular velocity, or its angular acceleration, or how far it goes through. Okay? But I brought this. This is actually uh, similar to the problem that we have. Here we have a thing that's allowed to rotate, and then I can apply a force at different axes. So I have this mass hanging, and it pulls on a string and causes this thing to move down. So I'm applying a torque to this object. In a similar way to this, where we have the shaft that's applying a torque to the rotating object, if I put a mass on here, it'll cause it to rotate down. So it actually accelerates. See it spinning faster and faster. But the nice thing about this is you can change its moment of inertia. Remember, moment of inertia is mr squared, so I have these little masses that are attached on these rods, and I can move them along those rods so that they're at different radii. So if I move these masses out to bigger radii, what's going to happen to the moment of inertia? It's going to increase a lot, right? Because my moment of inertia is mr squared, and so if I, this is maybe increasing that distance by a factor of 4 or 5, it's going to increase the moment of inertia by a factor of 16 or 25 because it's squared. So remember, this is accelerating at this rate. If I increase the moment of inertia by that much, how will it affect the rate of acceleration? Will it increase it or decrease it? It's going to decrease it, right? So I'm giving this a lot more inertia, which is going to decrease that rate of acceleration. My torque remains the same, but it's going to decrease the rate of acceleration. I haven't done this before. I think it's pretty traumatic. Not traumatic, but traumatic. All right, so let's see. Yeah, so we see it accelerates a lot more slowly than it did before when they were a lot closer. It just spins a lot more slowly. All right. So I would expect to see a Newton's second law problem, probably something similar to this. Look back at some of the old exams and in your homework, and you'll see some that are similar. All right, we have one more thing in this chapter that has to do with angular momentum. The angle and the conservation of angular momentum. Remember before we had linear momentum, which was P is equal to M times V. Everything okay? Okay, yeah, so the linear momentum is M times V. Well, the angular momentum, instead of being a product of the mass and the velocity, is going to be a product of the moment of inertia and the angular velocity. That is, say that L, which is the value that we'll use for angular momentum, is equal to I, which is a scalar quantity, times omega, which is a vector quantity. Okay, and again, we compare this with our linear momentum, M times V. So still we're doing this thing where we're sort of translating vector quantities to, or linear quantities to angular quantities. So just to remind you what we've had, I've written this before, but where before we had x, now we're going to theta, where before we had v, now we're going to omega, a to alpha. We went from force to torque, and so we equated our Newton's second law, F equals ma, torque equals I alpha. Where before we had mass, now we have moment of inertia, and now before we had momentum, it's not equal, but now we have angular momentum. The unit for angular momentum is going to be, let's see, what's that, kilogram meters squared per second. So nothing fancy, it's just the SI units for I and omega, the product. And just like with linear momentum, we have angular momentum is conserved. That is that Li is equal to Lf. So if I have no external torques, then the momentum of an object will not be changed. The angular momentum will remain the same. This comes up a lot, like with people that are doing gymnastics or people that are doing dancing of sorts. Cheerleaders do this a lot, where they change their moment of inertia and when they change their moments of inertia, it changes the way that they spin or that they rotate. So you'll see people that do this, like figure skaters do this a lot, where they'll throw their arms out as they're spinning, and that causes them either to slow down or speed up. So if a figure skater takes their arms and throws them out, what does that do to her moment of inertia? It increases her moments of inertia, right? So it increases her moment of inertia, which causes her to slow down. And we can see that here with our conservation of angular momentum. This is I initial omega initial equals I final omega final. That if a person goes from like this to like this, is able to throw their arms out, then their final moment of inertia will increase, causing their final angular velocity to decrease. See, I have a video here about the circus. Have we watched these circus videos before? Not sure if we have. Yeah, the PBS has a special series on the circus and the physics of the circus. And this is just a little segment about, I think it's about the acrobat and how kilograms and a radius of 1 meter, and it's spinning at 2 revolutions per second. And a kid then with a mass of 50 kilograms jumps on the outer rim of the merry-go-round. What is the angular velocity? So you want to ask yourself the question is, how does the moment of inertia change when this kid jumps on? And then how does that affect the angular velocity? We're going to treat this kid as just a point particle. So he jumps onto the edge of this merry-go-round. You'll just treat him as a point mass that falls onto the merry-go-round. Remember, a merry-go-round is a disk, which is a cylinder, so you'll need to look on your table to find the moment of inertia for that. All right, I'll stop at about 310. 310. Just guess if you're not sure. I'll go on to 315. let's see. It is D is the right answer. What I want to look at here is how my moment of inertia changes. This is the moment of inertia of just the merry-go-round. The moment of inertia of the kid, so we're treating him like a particle. So it's just mr squared. It's like the particles going around on the bar. Mr squared, so that's going to be 50 kilograms times the radius, which is 1 meter squared. So his moment of inertia is 50 kilogram meter squared. So the initial moment of inertia is 50. That's just for the cylinder. The final moment of inertia is 50 plus 50, which is 100. So I'm increasing my moment of inertia by a factor of 2. I've increased it by a factor of 2. I know that angular momentum is conserved. So I initial omega initial equals I final omega final. And I'm looking for omega final. So that's going to be 50 over 100, or 1/2, times the initial angular velocity, which is 2 revolutions per second, or 1 revolution per second. You want to look at how the moment of inertia changes. And when I'm looking at the kid here, the kid is just a particle on the edge of the disk that's spinning around. This is equal to 1 revolution per second. Also notice that I didn't need to change my units, that my units all sort of canceled out in the end and left me with revolutions per second. And since I was looking for revolutions per second here, I just left it in revolutions per second. All right. You will have angular momentum problem on the test. Uh, it'll be something similar to this, where I'm changing my moment of inertia. You have a couple homework problems that are similar, where you're changing either the mass distribution or the amount of mass, which changes the moment of inertia, and then asking you what is the new angular momentum. Alrighty, can do that. Probably about 5-10 points. Actually, on the test, the upcoming test, it's going to be sort of a normal length, but it's going to be a lot fewer points because you already got 40. Was it 40 points? I think on the take home. Was it 30? Yeah. So you'll just have 70 points on the test. So that's good for you. It'll be those points will be spread over a larger number of problems. So each probably worth less. All right. Let's see. I have a thing here. This is just a rotating platform. And stand on it, kind of doing like the ballerina thing. Y'all can try this after class if you want. It's actually kind of cool. I have some masses here. These allow me to change my moment of inertia a lot. So I'm going to sort of spin around. Actually, Lindsay, you think you could spin me? So just spin me around faster. Just sort of grab my arm. Yeah. I'm getting very dizzy. I know. Okay. Thank you. Do I want to try it? I get dizzy. I'm almost 40, so I get dizzy really easy. But okay. Did y'all ever do the up down dizzy out in the quad, like I said? Yeah. Sorry, just take me a second to. But anyway, I'm doing the same thing there, where I'm changing my moments of inertia, and when you pull your arms in, just like the ballerina or the figure skater, it causes you to go faster. All right, guys, there's a lot in this chapter. So we've seen kinematics, we've seen Newton's second law, both of which you'll have those. You also have angular momentum. Most of this stuff will be on the exam. In fact, I think, let's see, the last exam finished at chapter 6. Is that right? So we have 7, 8, and then the take home, and then we'll have optics on the next exam. All right, I think we have time to work through probably one of these problems for the take home. That way, if you want to work on it over the weekend, you'll have sort of a basis to start on that. Listen, chapter 9 is not going to be on the in-class exam at all. All of chapter 9 will be the take home. So I'm going to skip over this elastic properties of solids. If you're an engineering major, you're going to have whole courses on this. So you'll certainly see it again. But we were just sort of brushing the surface a little bit here. What these, we were talking about elastic stress and strain. It just talks about how if you apply a force to a material, it causes a strain in that material. It causes it to deform. We're just going to look at 1D. That is, if I apply a force per unit length like this, if I apply a force to it, it makes it longer. Or if you apply it in the other direction, it compresses it. So a lot of work that goes into determining how those materials are affected by different forces. But if you're an engineering major, which I know I have some of you, you'll have whole classes on this. So we're going to skip on ahead to the different statics problems, which is sort of the more of the basis of this chapter. Uh, Nothing new in this chapter, really just sort of different ways of looking at problems. We haven't done this as of yet. We've seen torques and we've seen forces in chapters, what, 4 and 7 or 8, but we haven't put them together. But if we have a body that's in equilibrium, um, we're going to look, equilibrium can either be uh, with an acceleration. Technically, an object is in an equilibrium if the acceleration is equal to 0, both the angular acceleration and the linear acceleration. But in this case, we're going to have static equilibrium where all bodies are at rest. So these are static problems. You can also have dynamic equilibrium where objects are moving, but they're not accelerating. But we'll just have static equilibrium. And because these objects are at rest, we have to have two criteria that are met. First is that the sum of the forces has to equal 0, and the sum of the torques equals 0. Now we've worked static problems for both of these where our torques are equal to 0 and our forces are equal to 0, but by combining those two equilibrium, which is true for any body at rest, we get a whole new host of equations which will allow us to solve for more unknowns. Um, so when you're solving these problems, I don't know, one must determine the net force for the objects and select a point of rotation that will eliminate the unknown variables. Really the tricky part on this is labeling all the forces properly and then picking your point of rotation for our net torque that will provide you an equation that will allow you to solve for the unknowns. Let's look at a couple examples. Hopefully we can get through this one today. Okay, I have a 5-meter ladder. By the way, this was similar to one of the problems that you have in your take-home test. Of a 5-meter ladder, it has a mass of 10 kilograms. It's leaning against the base 2 meters from the wall. So this distance here is 2 meters. I also know that I have a weight that is acting, a force weight that's acting upon this ladder. Where does the weight occur? Where does the weight, the force of the weight act on this ladder? Not at the top, no. Not at the bottom. At the center of mass, in the middle, right. So my force weight is going to act right here. I know that that force weight, by the way, is equal to 100 newtons, so I'm just going to go and write that. The weight equals 100 newtons. I have some other forces that are acting on this as well. In fact, I have 1, 2, 3, 4 forces that are acting on it. Now, two of those forces I know are frictional forces because it talks about the coefficient of friction between the ladder and the wall. So I need to make sure that I get the frictional forces that are labeled properly. Now, this ladder, if there was no friction, the top up here would move down and the bottom would move out like that. So what are the directions of my frictional forces? Here, what is the direction of the frictional force? It's going to be up, right, because the ladder would tend to move down, so the frictional force will oppose that motion. So the frictional force here will be up, and the frictional force here will be what? To the right, yeah. So let's go ahead and draw those two forces. I have a frictional force, I'm going to call it FSW for the static frictional force acting on the wall. Let's try to start this back. Yeah. And then down here, I have FSG, I'll call it. static frictional force acting on the ground. And then I have two other forces. What are they? They're sort of related to the frictional forces. The normal force, right. So I also have the normal force. In fact, I have two normal forces on this ladder. Where are they? Right. So remember back to normal forces. Normal forces are always perpendicular to the surface. In fact, normal forces are also going to be perpendicular to the frictional force in these cases. So my normal force here will be in that direction, and my normal force here will be straight up. So I'm going to label these forces FNW and FNG. FNW and FNG. I can also find the angle theta, so I'm going to go ahead and do that. I know that I have this triangle. This distance is 2 meters. It's a 5-meter ladder, so this distance is 5 meters. So I can find this angle theta. Theta is the inverse, what? Is it sine or cosine? It's the inverse cosine of 2 over 5, which is 66 degrees. And then I'm also told that the mu, the coefficient of static friction for the wall, is 0.5. I think that's all that I know. I also know this distance right here, I've already said, is 2.5 meters, because it acts at a point at the center of mass. All right. So now I need to write some equations. I can say the sum of the forces in the x and the y direction are equal to 0. Sum of the forces in the x direction is equal to 0. That's going to be FSG and FNW. FSG minus FNW equals 0. Those are my forces in the x direction. So I'm taking all these forces and I'm collapsing them down to a free body diagram, but I'm just looking at my x forces here and here, and in order for this to be in equilibrium, that it's not accelerating to the left or right or up or down, that the sum of all the forces have to equal 0. What about my y forces? Right, I have three forces, FSW, FNG, and FW, and those have to all add up to equal to 0. I'm going to go ahead and just sort of mark my unknowns as I'm going through this to remind me. FSG is unknown, FNW is unknown, FSW is unknown, and FNG is unknown. So already I have 1, 2, 3, 4 unknowns. Now actually I only have 2 unknowns because FN and FNW and FNG are related. No, I'm sorry, I have 3 unknowns. I have 3 unknowns because I don't know mu for the ground for FSG, right? But these 2 variables are related, but I have still that mu that I don't know. Or we'll see, it'll fall out in the equations. I'll show you in just a second. The third equation, and this is sort of the tricky part, is I can write 4 equations here, and I will. I can say that the sum of the torques about any axis is equal to 0. So I can say that the sum of the torques about an axis that is at the bottom is equal to 0. So I'm going to pick this axis, and I'm going to sum up all the torques. I need to remind myself what these angles are. So if theta is 66 degrees, I'm going to call phi 90 minus theta, which is going to be 24 degrees. So this angle will be phi, which is 24 degrees. This angle will be theta, and this angle will be phi. You'll follow me on that? How I get that? Like here, I know this is 66 degrees. I can imagine a triangle here. So this is 24 degrees. 24, 66, and then the 90 gives us 180. Here I have a line here that's parallel with a line down here. So this angle and this angle are complementary. They're equal to one another. So they're both 66 degrees. And here, if this is 66 and this is 90, which it is, then this has to be that minus 180. So this has to be 24 degrees. So a little bit of geometry in finding the angles, and you'll find a similar thing on some of the take-home questions. Just be careful with your angles and make sure that you get them correct. So the sum of the torques at the bottom, I have first a torque here. That is a clockwise torque, so it's going to be negative FW times 2.5 meters, that's our moment arm, times the sine of phi. And then I have two more forces up here. Both of them are going to cause a positive torque. So plus FNW times 5 times the sine of theta plus FSW times 5 times the sine of phi. And that's equal to 0. So I can write that equation. I can write a fourth equation. In fact, I could write a whole bunch of equations because I can pick any point about this axis and say that the sum of the torques is equal to 0. So let's pick also a point up here and say that the sum of the torques at the top is also equal to 0. And then I can write a similar thing where I say the force weight, let's see, that's now causing, is the force weight, if it's hinged about the top, is the force weight causing a clockwise or counterclockwise torque? It's a counterclockwise torque. It would cause the ladder to move in that direction. So it's counterclockwise. So I'm going to have positive FW times 2.5 again. But now this is this distance, 2.5, because that's the distance from the axis of rotation, times the sine of phi. And now down here, these torques, FSG is causing a positive torque. FSG times 5 times sine of theta minus FNG times 5 times the sine of phi. This angle right here is phi. Okay, so now I have four equations. I actually have another little set of equations over here where my frictional force Fs is mu times my normal force. So all of these normal forces and frictional forces are related to one another. And I can plug those back in. Now it's just a matter of solving it. So it's a big system of equations. I need to figure out some way to solve for the, what am I looking for? The coefficient of friction mu g. So I'm looking for what is mu g. Okay? I know that mu g, by the way, is equal to FSG divided by FNG. So if I can find both of those, then I'll have my coefficient of static friction. All right. You can solve this in different ways. Let's see, what did I do? First, I can find my FNW. If I look at this equation, mark all of my unknowns here. I know the weight, I know the angles, but I don't know FNW and I don't know FSW. All right, but I do know mu W. It's 0.5. So really, I only have one unknown in that equation, and I can solve it for that unknown. It'll look like this. If I take this, I'm looking for, I'll rewrite it just a little bit. I'll go ahead and put some numbers in. Negative 100, that's my weight, times 2.5 times sine of phi. Well, phi is say if he was 24 degrees plus FNW times 5 times sine of 66. I'm looking at this one right here, the torque on the bottom, and I'm going to solve it for FNW because that's the only unknown that I have in that. FNW 5 sine of 66 plus FSW is going to be mu s, which is 0.5. I get that from up here, it's given in the problem, times FNW times sine of 24. That's all equal to 0. Okay? Bear with me. So now I can solve this for FNW. I'll leave you to do the algebra on your own, but the FNW comes out to be 18 newtons. Because notice I only have one unknown now in this equation here and here, and that was because I knew that coefficient of static friction. So I could replace my FSW here with mu times FNW, and then solve for FNW. Okay, so now that I know FNW, I can look up here and say, well, gosh, if I know FNW, then I know FSG. Okay, let me step back through and I'll answer that question. But so let me blow this up a little bit. So I'm looking at the torques on the bottom. And listen, when you're doing this on the quiz and actually on the test, and actually on the test, the problem that I give you that's similar to this is a little bit simpler than this because it doesn't have all these frictions. But I wanted to see the friction and how it plays out. But you're going to work it in a very similar way. I'm looking at this, and I'm thinking about what are my unknowns in this equation. I know this, and I know this. I know all the angles. So really my only unknowns are FSW and FNW. But I also know the coefficient mu W. So really I can replace FSW with mu times the FNW. So really I only have one unknown in this equation because I can replace this with mu times the normal force. And then I have FNW, which I don't know, and FNW, which I don't know. So down here, that's my force weight, my distance, my angle. This is FNW times the distance times the angle. This is the coefficient of static friction, mu W, times FNW. So what I've done is I've replaced FSW with mu times the normal force. So this value is the coefficient of static friction, which is in the problem. What's that? Oh, yeah. Thank you. Yeah, so I need a distance here as well. Was it 5? Okay, yeah, so I need a 5 meters right there. Okay. Cindy, does that answer your question? The 0.5 is our coefficient of static friction. Okay? And then, as I said, we can come back up and look at our equations. Listen, on the take-home test, I want you to make sure that you have these equations very clearly laid out. And then once you get that, it's really just algebra and solving a system of equations. But once I get that, I can say, well, FSG has to equal FNW. So not only is FNW equal to 18 newtons, but FSG is also equal to 18 newtons. So I already have one part of my solution. Now I just need to find FNG. And to find FNG, let's see, I can look at my Y forces. Is that right? Yeah, I can look at my Y forces here. And I can solve that for FNG. So if I solve that for FNG, my Y forces, it's going to be FNG equals FW minus FSW. That's going to be 100 newtons. minus, I know that mu W, FNW, so that's going to be 100 newtons minus 0.5 times 18, which is what I found up here. That FNW is 18 newtons. So it's going to be 9 newtons. So 100 minus 9 is 91 newtons. All right, so that's my FNG. So this is going to be 18 over 91. And then I'm done. It's 0.2. That is my coefficient of static friction. Really, these are about writing your equations correctly, right? Some of the forces in the x, some of the forces in the y, and then picking an axis about which you can say, what are some of my torques? It's sort of funny because usually when we do torque problems, we have an actual axis that this thing is rotating about. But in these statics problems, since it's not rotating at all, we can say our axis is anywhere at all. I mean, you could pick this and say that your axis is here and do the sum of the torques about that axis, or here. But that doesn't really make any sense to do it that way, because then the trick is that you want to pick an axis where you lose out some of your unknowns, that you don't, those unknowns are not present in the equation. So FSW, FNW, for example, would be not present in the equation. And then it becomes just solving the system of equations. It's kind of tricky. You got to be careful. Just make sure that you lay it all out and you know clearly what your unknown and known variables are. But please, on the take-home, when you do this, make sure that you do it very neatly. I will give you partial credit for the take-home, but only if I can really tell what you're doing. All right? Think y'all could do that? Listen, I would set a goal for yourself, unless you're just swamped this weekend, that you go ahead and do that first take-home problem, because it's very similar to this one. Actually, you know what? I would try to do, not the first, I would try to go ahead and do your derivation and the third take-home problem. You see, it's very similar. There's no friction on it, but you have some other forces that are at work. You have a tension here, and then you also have a kid on the ladder. You're just going to treat that like a point source of mass, and he's going to have a weight then that will be pointing down here, and then you also have a tension that the rope is giving. Oh, the answer is 0.2. 18 over 91 is 0.2. All right, folks. Yeah, yeah. I know that algebra sort of gets bogged down in class, but as you're working on the take-home, if you need some guidance, you can see me. I'm not going to tell you how to do it, but if you have specific questions that I might be able to answer, I will. Okay? So we'll try to do that derivation and that third problem on the take-home this weekend, if at all possible. Have a good weekend. I'll see you Monday. What's that?